Good morning, everyone. I'm Haley Peterson. Welcome to Science Sunday on the Kitchen Table News Network. This is my co-host, Snickers. Have you ever been in the dark about something? Because your rod cells have been. Ha 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 ha. Today, Dr. Heinrich Messerschmitter is going to bring light to the subject of phototransduction, a subject that will hopefully light up your life. Dr. Messerschmitter is at his science lab, deep underground in an unnamed remote location. Let's join him now.
Good morning, all. I am Dr. Heinrich Messerschmitter. I have been asked to discuss phototransduction in the rod cells of the retina on this fine Sunday morning. I'm sure you all have wondered what makes seeing in the dark possible, especially when you can't find your flashlight. Well, the rod cells and their activity help us see light in a dark world. Phototransduction is the process by which the eye absorbs light and creates a neural response in neural noggin. First, a photon, the simplest unit of visible light, enters the eye and hits the retina. The retina contains photoreceptors called the rods and cones. The rods are very sensitive and can detect even the smallest amount of light, thus allowing night vision. During the darkness, the rods are at resting potential of negative 70 millivolts and are considered depolarized. While in the dark, depolarization causes voltage-gated calcium channels to open and allow calcium ions into the cell. To maintain the negative 70 millivolt charge, non-gated potassium channels allow a constant flow of potassium out of the cell. The sodium-calcium-potassium exchange pump also assists in keeping the membrane at resting potential. When the photon enters the eye, it is absorbed by the visual pigment called rhodopsin. Rhodopsin is made up of 11-cis-retinol and the protein opsin. The retinol actually absorbs the light, which then triggers a change in the configuration of 11-cis-retinol to 11-trans-retinol. The opsin activates a G protein called transducin. When the transducins are activated, GDP is changed to GTP, and GTP then acts as the activated G protein. The GTP stimulates the cGMP phosphodiesterase. This concentration of cGMP is precisely controlled by the interaction of cGMP and guanylyl cyclase. The activated phosphodiesterase hydrolyzes cGMP to reduce its concentration. The product of hydrolysis is a lesser concentration of cGMP, which causes the sodium channels to close. This results in hyperpolarization of the cell. At that point, cGMP activates the protein kinase G, terminating the phototransduction process.
Thank you, Dr. Messerschmitter, for your time. Well, that's it in a nutshell, folks. Phototransduction allows us to see in the scary darkness. Amazing, isn't it? Okay, now for the weather.